Yeah, thank you very much. So I'm going to basically continue from where Vaki left off. I suppose I'm obligated to say that this research was funded in part by the Fields Institute and NSERC, and from generous support from viewers like you. Please hire me, and please hire Vaki. Okay, so as Vaki said, we have 4 tasks that we're trying to do to build this theory of non-commutative stochastic calculus. We have well, first of all, we want some kind of analog of the semi-martingale, which will be expressed as a martingale plus some finite variation process. And then after that, let me get rid of this now. Okay. Then we will construct stochastic integral of where you integrate this semi-martingale-like process against a process of linear maps. And then after that, we'll try to build the quadratic covariation integrals, where you integrate a process of bilinear maps against 2 different of these semi-martingales. And then finally, we're going to build the Ito's formula, right? These are all sort of ingredients that are necessary to get Ito's formula, because in Ito's formula, you have both like the first derivative term, which is a stochastic integral, and then the second derivative term, which is this quadratic covariation integral. Okay, so before that, I think most of the people here are somewhat familiar with operator algebras, but just in case, here's a slide on the von Neumann algebras, right? So the von Neumann algebras really play the role of non-commutative measure space. And if you have von Neumann algebra with a trace, or perhaps more generally with a state, then these are basically the analog of probability spaces in the non-commutative setting. And the ones with the trace have a lot of stronger properties that are more resemble the finite measure space. So von Neumann algebras, well, they're star subalgebras of B of H, and they're closed in weak operator topology. And then we have this trace, right? So a faithful normal tracial state, if you will. So it has this state, so it's positive, just like if you had in classical probability, expectation of x squared is positive. It's faithful, so like if that the expectation of x star x is 0, then x has to be 0, and the expectation of 1 is 1. And then it's tracial, just like trace on matrix algebra. Trace of xy is trace of yx. And it's normal, meaning it's continuous with respect to this, say, sigma weak operator topology, which is kind of the natural topology for the von Neumann algebra, which, by the way, this sigma weak operator topology should correspond basically to convergence in measure for L infinity functions. So it kind of, again, this is very natural to mimic the properties of the classical probability space, right? And so, and in fact, the classical probability spaces give you an example of this. And instead of filtrations of sigma algebra, right, since we can't refer to points as much or to sets as much when we non-commutativize the probability space, well, we have to take a filtration of von Neumann algebras as the corresponding to what we had in the classical case, these sigma algebras, right? So they're just nested. You can make various assumptions about the filtrations, but the filtration itself just means they're nested in this way. And in the classical case, this filtration is just given by L infinity with respect to the sigma algebra Ft. Of course, when you're doing the filtration, you naturally will condition on earlier times. So it's also good to mention here that when you have tracial von Neumann algebras, there's a unique trace-preserving conditional expectation. This conditional expectation is automatically normal and behaves all the way that you would want for a conditional expectation. And here, the expectation of x given b is the notation I'll use for conditional expectations. Okay. Now, again, since we don't have points, we can't like make pointwise statements, but rather we have to view all our elements as a element of some LP space. And so we're going to have processes where, for each time you have an element of the LP space. And the LP space for the von Neumann algebra is defined, you take this p norm, you take the absolute value of x to the p, take the trace of that, and then take the piece, the root of that, and then the completion of this is one definition of the non-commutative LP space. All these LP spaces fit together in a similar way as for classical probability. In fact, if you study the affiliated operators for the tracial von Neumann algebra, this actually gives you an analog of the, say, L0 space of measurable functions that are finite almost everywhere. And I think, I encourage you to learn about affiliated operators at some point. It kind of gives a good unifying perspective where all these spaces fit together. This is also another thing where having a finite von Neumann algebra actually makes a difference here, because if you have a general von Neumann algebra state, you don't actually have this affiliated operator picture as much. Now, if these LP spaces, they satisfy analog of Holder's inequality, this is a pretty well-known fact in a lot of operator theory. But if you have x's and if they're in these various LP spaces, then multiplying them together makes sense because they're all inside the affiliated operators, and then the p norm of the product is estimated by product of p norms here when these exponents add up in this way. And the conditional expectations are also contractive in LP, so they play nicely with everything. Now, there may be some people in the audience, I know there's certainly people in random matrix theory who don't know that much about the technical background of von Neumann algebras and want to just formulate the statements in terms of C-star algebras to, say, minimize the amount of prerequisites, which is understandable. Now, if you're talking about LP spaces, it really doesn't make that much difference, because if you take your C-star algebra and you define the p norm and then take the completion, then you really just recover the same thing as if you took the first completed your C-star algebra to a von Neumann algebra, right? You take your C-star algebra and you have its trace, you have, you pick a trace on it, you take the GNS representation, and then that generates a von Neumann algebra. And the LP of that von Neumann algebra is just the same as if you took the C-star algebra and completed it in the LP norm. And so basically facts about the von Neumann algebras, since the C-star algebra gives you the same LP space, you could also just state more generally as holding for C-star algebra. So in case I don't know, if you don't feel that comfortable with von Neumann algebras, I mean, you just think about it in this way if you want. Okay, so with that background out of the way, now we try to define this analog of semi-martingale. And as Vaki mentioned, classically the semi-martingale is the sum of a local martingale and a process which has locally finite variation. And so we're going to define a similar thing. We're actually going to take, we're actually just going to take a martingale plus an SV process. Okay, so first of all, what does it mean for the process to be adapted? That just means that, okay, so you have this process for each time in R plus, by which we mean like the closed interval from 0 to infinity. It spits out an element in the LP space of your tracial von Neumann algebra. And adaptedness just means that at time t, it lands in the tth element of the filtration. Now, then when we talk about martingale, what does martingale mean? So, well, martingale is supposed to be adapted, and the martingale property is that the expectation of it given an earlier time is the same as just the value of the process at the earlier time. And by the way, this formula, I guess, already implies that it's adapted, right? Because MS will automatically be in this AS because it's the conditional expectation. Okay, so then the finite variation process, well, it's just an adapted process that has locally bounded variation with respect to norm p. Right, so this is just in a sense of you have a function from an interval mapping into some Banach space, and then it makes sense to talk about if it has bounded variation. Right, you just look at you take a partition and like add up the sums of the norms of the differences and demand that this is bounded. well, sorry, I guess I mean here LP of A. This is a typo, but yeah. So just LP of that C-star algebra or of von Neumann algebra. Okay, so then we don't claim that we have fully solved the problem of what is the analog of a semi-martingale, but we have mimicked this decomposition, and so we define this notion of a decomposable process, and we can actually take the martingale to be like an LP martingale, and take this to be a finite variation process in LQ, and define this decomposable process. And we're also here assuming, wait, this is, I don't understand where this point. Okay, that we're assuming here that this is continuous and that this is also continuous. In general, you can deal with things that are not continuous. For instance, certain Lévy processes, even like a free Poisson process, it would also not, it wouldn't really satisfy this continuity condition. But for now, we're focusing on the continuous case. This covers a lot of stuff, in particular, a lot of Brownian motions. And I'll also remark here that this decomposition here turns out to be unique, provided you have certain conditions on the exponent. But in general, it may not be unique. But if 1 over p plus 1 over q is less than or equal to 1, and if you make a choice of normalization at 0, then it is unique. So one thing that's nice about this general non-commutative framework is that it encompasses also classical stochastic processes. So for instance, and you can do matrix valued classical stochastic processes, and this will fit into the same framework. Right? And this is a good thing if we're going to if we want to prove some theorems about the matrix SDE converging in the large N limit to the free version, right? If we can fit them all into the same framework to begin with. So if you had a classical probability space and filtration, then you can consider the von Neumann algebra, which is L infinity from that probability space into n by n matrix algebra. Right? And then the filtration will just be the original filtration functions from the L infinity of the original filtration into the matrix algebra. And then the state, of course, will be the expectation from the classical probability space composed with the trace. So then if you had, for instance, just a classical LP martingale from your probability space into the matrices, then the process that Vaki described, where you just view this as a map from the positive real numbers into LP of the probability space, then this will be a non-commutative LP martingale in this sense up here. So you can basically fit in classical random matrix processes into this theory, and this also represents a sort of unification of the classical and non-commutative stochastic theory. I mean, I don't know if we've really fully completed this unification yet, but this is a major step in this direction. So other examples that you can get, say if you take a process with freely independent increments which have trace 0, then this will give you a martingale. This, of course, includes all the free Brownian motions and free Lévy processes. You can also look at D tuple of Brownian motions, look at this multivariate case, and the way you do this is simply to replace the original von Neumann algebra A with direct sum of several copies of itself. So in fact, really, stuff that we write for just a process taking values in A, it can automatically extend to tuples because you just replace the von Neumann algebra with a direct sum, and then this kind of saves us some notation in the general case. Moreover, you can have the Q Gaussian Brownian motion, and this is also an example of a non-commutative martingale. In fact, Vaki is working with several other people on projects related to this. Yes. In what sense? I don't think that gives you a martingale. I mean, I think there's some kind of analogy there, but it's not exact. It's not really a conditional expectation. But yeah. Okay. So great. So now we're going to try to construct the stochastic integral, right? So we know which processes we're doing, and then we want to do stochastic integration against this process. And in order to do this, our approach is by looking at linear maps and more generally multilinear maps. So we want to understand what linear map we're applying, what linear map we will be applying to the stochastic process here. And so we want to describe adapted processes of linear maps. So, and in general, you can have this linear map have a domain which is one algebra A with some filtration, and have the codomain be a different one. So for instance, this might be useful if you were considering something that was given by like multiplying on both sides by some rectangular matrix, right, which might change the dimension of which matrix algebra you want. Right? But, often you will have the A and B be the same, but there are cases where you might want them to be different. Now this adaptiveness means that if you have any time t and u which is greater than or equal to t, and if you were to take the output of the linear map on some A and take the now I think I forgot here. I should write lambda sub t, right? So lambda sub t, you apply it to some A, and then take the conditional expectation onto time u. And that's the same as if you took the conditional expectation onto time u inside here. Yep, and both sides here, this should be lambda sub t. Oh yes, okay, sorry. Right, sure. Right, and adaptiveness means that at time t, the linear map is in this space here, which preserves the conditional expectation for all u greater than or equal to t. Right, so adaptiveness means, yeah, exactly this, right? H of t is in this t filtration here. So here what we're writing, this notation is convenient because it gives us a notation just to say, you know, an individual linear map is in like the, you know, the filtration at time t. So there's a filtration of the spaces of linear maps corresponding to the filtration of the original C star algebra. Okay. Mm-hmm. Well, okay, I mean, I think you could make the definition with completely bounded things and it would work the same. And I mean, maybe it's all. No, but I mean, why is it bounded not from A to B, right? So you want. We're not trying to view this as a tensor product, right? So by the way, that means the next comment here is like, yeah, in a lot of previous work, you were considering derivatives which were elements of tensor product, and the element of the tensor product defines a linear map by the left and right multiplication. Now naturally, if you have these xj and yj in here to be elements of the von Neumann algebra, then by the non-commutative Holder inequality, this will map like the LP space into the LP space. But in our approach, we're emphasizing the linear forms because this actually gives us more flexibility than just defining the tensor product. Because if you define a tensor product, it's a very difficult thing of how do you choose the right norm. And maybe there isn't actually a good choice here. Because what we need to get out in the end is Ito's formula. And if we understand how to do this in terms of bilinear maps, then maybe this could inform us what sort of tensor product we might use if we can kind of formulate it in this way. But ultimately, like, we want something more general than tensor product, and this also includes examples where instead of just looking at the derivative of a non-commutative polynomial, you use trace polynomials where you have some terms where we multiply by trace. But I think no. This is the thing in the domain, right? So I'm not saying, so it's not that the xj is an LP and the yj is an LQ, right? It's that the input is an LP, this A is an LP, and the output will be in some space. So it's not like an issue of right multiplication versus left multiplication. It's just we have a linear map. We take something in LP, we transform it in some way, and get out something in LP. Let us not have a 10-minute technical discussion now. Let us go on to talk about how we use it. Okay, so, right. So we're trying to construct a stochastic integral. And as with a lot of things in functional analysis, you don't necessarily immediately define your thing on the whole space that you want it to be defined on. You define it on the dense subspace and then try to extend the definition by continuity to the whole thing. And so in particular, what we're going to do, we're going to first restrict the types of linear maps we're studying to so-called elementary predictable processes. This is a quite a standard thing to do in the construction of stochastic analysis. And then we're going to get some bounds so that then we can extend it to more general H. And then finally, at the end, we'll show that actually the Riemann-Stieltjes sums that might give you a good intuitive definition of what this is actually converge to this thing. Right? So maybe at the last step is the thing that you maybe want to use in practice, but then we have these stages of the construction. So elementary predictable processes, that's processes where you have these linear maps, and basically it's constant on some certain intervals. So you just build this up as a step function. And the HIs are chosen so that they're in the appropriate elements of the filtration of linear maps in order to make this thing be adapted. And the integration of this is automatically easy to define because you're integrating a step function against the xt, and so therefore you'll just add up over each of the elements of the partition. You'll add up the corresponding x, the increment in the x's. And here I have this ti minimum capital T just because I'm fixing a partition of all the positive numbers, and yeah. And really, I want to think of this integral thing as a process depending on capital T. So really, so in a sense, I'm writing out this formula uniformly for all values of capital T. But if you only just fixed the value of capital T, you could just imagine you had a partition of the interval from 0 to T, and then ignore this minimum with capital T. Okay. But no, this is how you construct it. You just take each of these increments, and in this formula, then you're just cutting off at capital T and not doing anything beyond there. Okay, so there's some objects in stochastic analysis called the Léon measure, which which is related to the Ito isometry. And what we're doing here, we don't immediately get a version of the Ito isometry, and part of it has to do with this limitation of like that we don't have a proper tensor product to do things on, and in the end, after discussing quadratic covariation, we can get to some version of Ito isometry. But for now, what we're doing is just replacing the equality with inequality. So the point here is we want to estimate the L2 norm of the stochastic integral by something over here. And so then if we have h's which converge with respect to the norm defined on the right-hand side, then we'll get that these stochastic integrals converge, and so then we'll be able to extend to a greater class of h's for this one. So the first thing to note here for this measure is the following, that, okay, if you can define a measure on the real line. There's a classical theorem about this, that if you have some kind of quantity to just measure to assign the measure of a half-open interval, then you can construct a Borel measure on the real line from that. Basically, this relationship between a measure on the real line and the cumulative distribution. And if you have a martingale, then the increments of it are orthogonal. And so that will mean, by the Pythagorean theorem, that, say, xt minus xs, norm 2 squared, that this will always be greater than or equal to 0, and that this quantity will be additive when you add up different increments. And so therefore, you can define a measure on the real line that assigns the measure of each interval as the L2 norm of xt minus the L2 norm of xs, each of them squared. And that measure is what you use to control this stochastic integral. So basically, in a lot of the talk now, I'm really going to restrict to the case of a martingale, because in the case of the semi-martingale, where you take the martingale and add a finite variation process, the finite variation process terms are dealt with in their own way, but it's usually strictly easier than the stochastic term. So it's really the stochastic terms that we have to worry about. And I don't want to make the talk infinitely long, so I'm going to restrict to the martingale part and focus on that. Right? And so for the martingale part, we have this measure here, and we can estimate this by this integral here. And the proof of this is really just, you look at this, it's an elementary process, so you split this up into each of the little intervals, and the piece from each of the interval will be orthogonal because of the adaptedness property and the martingale property. Right? Each new interval will basically be orthogonal to the algebra at the previous time, and so then these will all be orthogonal, and you can just add up the increments with the Pythagorean theorem, and then estimate each of the increments individually and add these up and get this integral here. And so what this allows us to do is, well, now we can define a norm by just looking at the L2 norm with respect to this measure, kappa x, of the appropriate norm of HS as a map from L2 to L2. And then I of x is just going to be the completion of these elementary predictable processes with respect to such a norm like this. And then by continuity, this stochastic integral mapping h to the integration here will extend to this larger space. Then finally, we have this limit formula. The limit formula is that, indeed, if you take these Riemann-Stieltjes sums and you take here the left endpoint of each of the intervals, then as the mesh of the partition tends to 0, this will converge to this stochastic integral defined in the previous step. Right, so I'll remind you this notation, as Vaki mentioned, we're looking at the partition as a list of points, and then if t is a point in the partition, not including the 0, then t minus is just going to be the previous point, right? So each of the little intervals in the partition is the interval from t minus to t. Okay, so that completes the second step of what is stochastic integral. Then we have the step of what is quadratic covariation, which is going to enable us to define the Ito correction term in the Ito formula. And the construction of the quadratic covariation follows a similar sort of outline, where you first try to define it for processes which are easy to understand, and then you prove some kind of boundedness estimate, and then extend it to a larger space. And in fact, in the paper, we actually do 2 iterations of this, like 2 iterations of extending it to a larger space, because it's actually quite technical to try to do. But the basic idea is kind of the same as what we did before. Well, first of all, we want to look at the appropriate processes of bilinear maps that we could apply the construction to. So we're going to end up considering not maps from L2 to L2, but actually maps from L2 times L2 into L1 of the operator algebra. And the reason for that is the motivation of the following example. And I think I realized I completely changed the notation from last time, but the point is, you have a map, a bilinear map that's given where you take 2 inputs, x and y, and then you multiply some terms on the left and in the middle and on the right. And this mapping that sends x, y to some linear combination of products like this, this would be a canonical example of a bilinear map you can consider. Now, the problem is, if you wanted to say, okay, well, we do everything L2 valued, you run into a problem. Because if you have something in L2 and something else in L2, and then you multiply them together, say these AJ, BJ, and CJ are, say, in L infinity, you multiply them together, and the product is not in L2, right? The product is in L1. You don't run into this problem in classic stochastical analysis as much, because the spaces that you're mapping into are like finite dimensional vector space. And it doesn't matter what norm you use on finite dimensional vector space. But if you're mapping into von Neumann algebra, then multiplication is not a bounded map with respect to L2 norm on the domain and the target space. Right? So you have to choose the correct P norm so that the multiplication makes sense. And so these most natural examples will not give you bounded map from L2 times L2 into L2. And for that reason, therefore, we want to say, from L2 times L2 into L1. Or you could more generally take other choices of exponents P, where you have your 2 exponents P over here and a third one over here that satisfy the right relation that you add up the reciprocals to get the one for the output. Okay, so that's why we have processes which are mapping from L2 times L2 into L1. So as I mentioned, you also can consider other P's. So if you consider some 1 over P1 plus 1 over P2 equals 1 over P, then such process where you do left and right multiplication, then you'd expect that naturally to be bounded from LP1 times LP2 into LP with this, if you have these conditions. And in fact, what we're going to do is that we can define a norm where you take the supremum of the norms as bilinear maps for these different values of P, and take the supremum over all such values of P between 1 and infinity that satisfy that relation. And by the way, if you're familiar with interpolation results in real analysis, basically, if you have the boundedness kind of on the edge cases where you had some of where the P's were equal to 1 or infinity, then this will automatically bound all the other values of P as well. And one of the motivations for this came in my joint work with Wu-Chun Li and Dimas Liaktenko, where we studied some non-commutative version of smooth functions, where we based it on trace polynomials, and we exactly used some norms like this, where we took the soup over different values of P. Because if you consider iterated differentiation, you have to differentiate it an arbitrary number of times, and you need some kind of boundedness of arbitrary size multilinear maps, right? And you can't fix which P you want in the domain, because if you have a larger and larger map, then and you need the 1 over P's to add up to something, then you need your P to become larger and larger. So then in the end, we just said, okay, whatever. We'll just consider all possible P's and estimate the norm with respect to all of them and use that for our norm. Okay. So in the end, right. So now we're looking at these bilinear maps. We've defined a norm that we can use for them, and then we want to define adaptedness. So adapted, I think Vaki mentioned this a little bit as well. Just like we did for linear maps, we do adaptedness by saying that you take the conditional expectation of the output is going to be the same as if you took the conditional expectation of the input. And we do this for each of the inputs individually, coordinate-wise. So we say we take the, so if you take b to be, so let's say, so we have u greater than or equal to t, and we have this lambda of t. And if the second coordinate b is already in the use element of the filtration for b, and then we take the conditional expectation onto the use element of the filtration, then this will be the same thing as if we took the conditional expectation onto the use element of the filtration inside onto the A, right? As long as the B is already in the use element. And similarly, the other way, if the A is already in the use element of the filtration, and then you take the conditional expectation of the output onto time U, then that's the same thing as if you did this inside to the B. And you can check in the previous example where the bilinear map is given by multiplication on the left and right that this property will be true, because this basically just follows from the bimodule property of conditional expectations of the von Neumann algebra. And at this point, having seen what we did for linear maps and for bilinear maps, you can probably generalize to arbitrary multilinear maps, right? It's the same thing. You want some kind of boundedness on products of LP spaces, and you want like adaptedness in each of the coordinates individually. Okay, so now we finally get to the quadratic covariation. And how does this work? So I'm going to state the end result this time of you take Riemann's Stieltjes sum and take limit, and then you get what you want. Right, so this is the end result of the construction. Actually, what am I? No. Well, okay, yeah. I guess all the versions are stated in basically the same way. Yeah, the end result is you can take some limit. But in each iteration here, I'm going to tell you like more and more general processes that you can plug into it to make this work. So here I'm starting with x and y, which are continuous in L infinity, like continuous in operator norm. So for instance, like a semicircular Brownian motion would do this, but not necessarily a classical Brownian motion, right? That's not continuous in L infinity. Right, so we're just starting out with pretty strong assumptions there. Now we're going to also assume pretty strong assumptions about the lambda. So the lambda, say, it will be left continuous, and it will be locally finite variation in this norm here. Now, ultimately, for quadratic covariation, we want to define it, and we don't want to have to make such strong assumptions about the lambda, right? But this is just what we're assuming in the first step. So we're assuming it's locally finite variation with respect to this triple norm, which accounts for all the different values of p. So then we take a partition, as Vaki mentioned, we have this notation for partitions, and then we have this Riemann's Stieltjes sum, quadratic Riemann's Stieltjes sum, where we take the bilinear map and apply it to the increment of x and the increment of y. And here, since we're doing this as a process as well, this is really the Riemann's Stieltjes sum, where you're kind of truncating everything to the interval from 0 to t. And so this x upper t and y upper t are just the x's where you stop them at time t. Okay. Now, if you don't want to worry about the t, I mean, you could just think about if you were to integrate from 0 to infinity, then you would just remove the upper t here. You would just take the overall quadratic Riemann's Stieltjes sum. Okay, and then this here, this is the thing we want to define, and we want to define it as the limit as the mesh of the partition goes to 0 of such Riemann's Stieltjes sums up there. And we claim that this limit will exist where you measure the outputs of this in L2 norm, and you do it uniformly over compact intervals of time. right? So you look at the L2 norm of the output and then measure it uniformly on intervals of time. Okay, so how does this work? As Vaki talked about in his talk, there's this Ito product rule. And the Ito product rule is basically, what you would expect from Ito formula if you apply it to a bilinear map of x and y, that you would get, d lambda and then lambda dx y and then lambda x dy, and then this is the sort of stochastic term with the quadratic covariation. And here's the same thing written in integral form. If you were to take it from time 0 to time t, this should kind of, I guess since I wrote t here, maybe I should write t here as the upper endpoint rather than the dot. Okay. Hey, but this is sort of what you would expect from product rule, and you could just try to write this out with the Riemann-Stieltjes sums and prove this. And for quadratic covariation, this last term is the so-called putative quadratic covariation. It's the thing we want to define. And so what we want to argue is that all the other terms, like this term and this term and this term and this term, already make sense. Okay, so this first term definitely makes sense because it's just a difference of the endpoint. This term makes sense because, like we assume that the lambda has finite variation and is continuous, left continuous. So basically, this would just be a Riemann-Stieltjes integral, like vector value. We kind of know that the d lambda makes sense in terms of Riemann-Stieltjes integration. And these two terms here are basically stochastic integrals because we have a dx here, and then this lambda and this y can be, we can apply the stochastic integral to the linear map where you take lambda and plug in y into the second coordinate. And then that's a linear map in the first coordinate that we can apply our first stochastic integral theory to. So the point is, these two terms make sense from stochastic integrals. This term makes sense from just general vector valued Riemann-Stieltjes integrals, and then this makes sense. And so therefore, the only remaining term has to also make sense in terms of the Riemann-Stieltjes sums for that thing have to converge, and thus this is how we prove. Okay. And then at the second step, we extend this further. So what do we do here? Well, so now instead of just starting, so we start out with, so we're going to study lambdas, which are limits of the lambdas that we had before in a certain norm. And we're going to study x and y, which are limits of the ones that we did before in a certain norm. So if we have locally uniform L2 limit of L infinity martingales, that's, so the L infinity continuous martingales are the ones we had before. Yeah, I should. And then we're just going to take x and y to be locally uniform L2 limits of those things. And then we're also going to take locally uniform limits of the lambdas, where at each time you're measuring the norm in bounded operators from bounded bilinear maps from L2 times L2 into L1. And if you take limits in those norms for x and y and this norm for this, then you'll be able to estimate the Riemann-Stieltjes sums uniformly. And so then, therefore, you can kind of extend the definition of the quadratic integral by continuity. So all this is, okay, this is like some really fancy spaces or seemingly complicated definition, but the idea of the proof here is just that you can exchange limits if one of the limits is uniform. Okay, so so if we do an estimation on the Riemann-Stieltjes sum, then we'll be able to get that the limit with respect to the x and y and lambda, which converge with respect to these particular norms, that this convergence will be uniform. And so therefore we can exchange the limit over partitions pi with the limit over doing the x and y and lambdas and taking the completion of the space. Right. So this is really all it is, that if you have two limits and one of them is uniform, then you can switch them. And so then we basically extend this to a larger space. And then you can do another extension And I mean, it's similar to the case where you were looking at integrable processes in the stochastic integral, where you define a space of integrable processes depending on x relative to these measures here, which I think I should have written x and y here rather than m and n. But you know, if you take limits with respect to L1 loc in this measure space, you can also do the same sort of argument. Okay, so all of this is kind of messy, and this is more general than versions that have done before. And our goal, one of the main goals at this point, is just to make sure that it's general enough that it includes reasonable C2 functions in Ito's formula when we try to prove Ito's formula. Okay, so overall, I don't expect you to remember all this, but the whole point of this quadratic covariation is, you know, we prove some bounds and then extend it to larger spaces, and in the end we define a quadratic covariation that makes sense for applying a bilinear map to the dx and the dy. Okay, so finally we can actually get to Ito's formula. Maybe I'll first remind you Ito's formula. Right, this is our goal, Ito's formula. We described what this term means from stochastic integral. We described what this term means in terms of quadratic covariation. Right, provided that our f is so provided that we make assumptions on our f, which will guarantee that this df and this d squared f are adapted linear maps and bilinear maps, respectively. So that's our goal now. We got to try to define what assumptions we need on the f to make this work with our technology of stochastic integral and quadratic covariation. And again, here below is what it's written in integral form, right? So in integral form, it's just f of xt minus f of x0 is the stochastic integral of df of x of s with respect to dx, and then the quadratic covariation integral of second derivative of f with respect to dx and dx. Maybe I'll take a short pause here. Stare at the Ito formula. So now we have to just describe what kind of f will make this work. Okay, so now this is also somewhat technical, but okay, so first of all, what do I want for the C2f? So first of all, as Vaki mentioned, we have this notions of Frechet derivative. The Frechet derivative is kind of like the analog of the definition of differentiability that you would have in calculus, where you define it in terms of, you know, you have a tangent approximation with some linear map plus like little o of x minus y or something, right? But now the linear map is like a bounded linear map on some kind of Banach spaces, and then the error like it just depends on the norm of x minus y. Okay, and in particular, being C2 in the Frechet sense would mean that you have second order Taylor expansion. So you have, you know, f of y minus f of x is df of x times the difference, and then d squared f applied to these two things, and then little o of x minus y squared. And so this will be true for each point x, and then these two df of x and d squared f should be continuous functions of x, right? So that it's C2. That's just the C2 in the Frechet sense as elements of, you know, on the Banach space. You take your von Neumann algebra with operator norm and view it as Banach space and look at Frechet differentiation. Okay, but then we want to add some conditions on top of that. So because we're trying to look at these triple bar norms, where we look at different p norms, then we just want to assume that these maps, you know, that first of all, yeah, that the triple bar norm of this d squared f is finite, and that this is continuous in x with respect to that norm. Now, I guess I didn't technically write the definition of triple bar norm for the first derivative, but in that case, what it is just take the sup of the norms of this as an operator from LP into LP. You take the sup over P. Okay, so we have this triple bar norm where you're allowed to vary the P's in your LP space. and then you just demand that it's continuous in those. And then you have adaptedness, and the adaptedness will be, okay, that if you plug in points from the Tth element of the filtration, and then you have U greater than or equal to T, then you will be able to do the conditioning onto time U. I guess this here should be U. But yeah, so this is just the same as the definition of adaptedness for the linear map and for the bilinear map here, right? Where now, because this is a function, you just have to plug in inputs that are in AT. So then, with those assumptions, then these terms here will make sense in terms of the theory we've developed so far. So I see, yeah, there's not that much time left, but I think I have enough time to get to what I wanted to. So, how does the proof of Ito's formula go? And what I want to emphasize here, I mean, maybe interrupting this technical exposition, is, okay, what is our overall goal here? So previous versions of Ito's formula in the non-commutative setting, as Vaki mentioned, often don't really separate out the d squared f term and the quadratic covariation term. Right? It's sort of like, okay, we know what the analog of this whole thing is, but we don't know what the analog of these things individually is. And so you can prove this in special cases, like especially if you have free Brownian motion, then yeah, you can evaluate what this is. If you have Q Brownian motion, well, then it becomes a whole mess of combinatorics, but in a sense you can sort of think of what the thing is that you would put here. Right? But our goal really is to separate out the d squared f and the quadratic covariation term, and so then we could say, okay, well actually we're just going to compute one of these things individually. We don't have to think about the f and think about the x at the same time. You can just kind of isolate them. So then overall, this should give us more flexibility to be able to apply Ito's formula to more things. And this, of course, does encompass a lot of the previous versions of Ito's formula in the non-commutative setting that various people have proved, which Vaki mentioned in his slide. Right? And so what we really want to happen now in the proof of Ito's formula is that it will follow the proof in the classical case. And the proof in the classical case is that you do the Taylor expansion of f, and then you estimate each of the terms, and then kind of show that they converge to the things that you want. Right? And previous versions of the non-commutative case didn't actually follow this blueprint because they were viewing this all as one thing. Right? So with that in mind, we're trying to prove it based on the Taylor expansion. So we're going to be looking at Riemann-Stieltjes sums associated to a partition. Each little interval in the partition, we will use our Taylor expansion for. So we'll have a f of xs minus f of xs minus. We'll have the first derivative term in the Taylor expansion. We'll take the second derivative term, and then we'll take remainder term. So the way that I've formulated in here is basically with the integral remainder. So I separated out the second derivative at the point s, and then here I have the second derivative at the point s minus, and then like the interpolation between x of s minus and x of s, and this integration here. So this is just Taylor's formula with integral remainder applied to the Frichet differentiable function. And so then, okay, so then each of these terms we're going to sum up over the intervals in the partition and then take the limit as the mesh goes to 0. And if you sum up these things here over the partition and then take the mesh to 0, this is just giving you the stochastic integral term. Right? That's just giving you this. And if you do the same thing for this, if you sum this up over the partition and then take the limit, that's giving us this term here. Right? So the way we constructed the quadratic covariation, we made sure it included this type of thing here, because this bilinear form will be continuous with respect to the triple bar norm. So the previous results apply. Okay, so those are the terms that we want, and then we have this remaining term, which is the error term, and we just have to show that if you add this up over the partition, then this error will go to 0. So how does this happen? Well, probably goes exactly as the way that you would expect. Well, you assume this is C2, and so then you estimate the difference of the second derivative at these 2 points using the continuity. So here we're going to estimate this, with respect to triple bar norm, and then we're going to estimate the delta Sx with respect to L2 norm. And so in this case here, well, the triple bar norm is not. For this computation, we only really need the norm of this as a bilinear map from L2 times L2 into L1. Yeah, but the triple bar norm dominates that norm. And so we have this estimate here. And, well, L2 norm of delta S of x, that's basically this measure associated to the martingale x applied to this little interval. And then this here by continuity, okay, so you use a continuous function on a convex set is uniformly continuous. So you look at like a d squared f composed with x as a function of time. And so it will be uniformly continuous, and let's say omega is the modulus of continuity. And so this is basically just saying, okay, if the mesh of your partition is this, then omega of this is the largest that this difference here could be. Yep, and then this will go to 0 as the partition goes to 0. So in fact, if you sum up over the intervals in the partition, well, then you'll just be adding up these little measures, and you'll just get the modulus of continuity times the measure of the whole interval. And this modulus of continuity, it will go to 0 as the partition goes to 0. Yep, so all this is Taylor's formula in controlling the error term using the continuity of the second derivative. Okay, so I see I am out of time. I wanted to mention quickly, some examples. As I said before, you can study multivariate setting by taking your algebra and replacing it with a direct sum of several copies. And then the so-called single variable formulation in all the previous statements just actually includes that. Yep, and in the Ito's formula, one of the most canonical examples of functions you would consider would just be non-commutative polynomials. Yep, so of course, the formulation that we have done includes that case, so that in that case, you can describe this Frechet derivative in terms of the Voiculescu free difference quotients. Right, so this linear transformation, the f here will be basically just given by taking this difference quotient, which takes values in tensor product, and then doing the hash operation where you multiply on the left and right, and to get a linear transformation. And similarly for the second derivative. And so in particular, the Ito formula that we have above, it does recover the other Ito formulas like of Bion and Speicher, for instance, once you, compute what the quadratic covariation of the semicircular Brownian motion is, right? But so what we're saying is, okay, you have general Ito formula, you figure out what is quadratic covariation of semicirculars, and you figure out what is the derivative of the polynomial, and you plug those into the general Ito formula, and then you get this other version. You can generalize this to trace polynomials. These are functions where you multiply several traces together with a non-commutative polynomial. And as I mentioned before, there's this notion of trace CK functions where you kind of take limits of trace polynomials with respect to CK norms, which are defined by looking at these as different maps between different LP states. As Vaki mentioned, some applications, there should be applications here to the study of free Gibbs laws and to the study of non-commutative transport. I'll also mention Vaki had some previous work describing in a lot of detail, if you take a single variable function and apply it through functional calculus, how do you tell if that operator function is smooth enough to apply the theta formula to? Well, we have some a pretty good understanding of how that works as well, which you can ask Vaki about later if you want. And so in future work, we decide we want to build on this to SDE theory, as well as apply this to looking at random matrices. And in general, we might want to work on non-commutative stochastic control problems as well. Okay, apologies for going over time.